All right, dude, we are live. What's up, guys? This is Dem Keys, and today we are going to continue learning about how PWM works in the ESP32 using no STD Rust. Um, yeah, that's about it. We're going to be continuing with that. I've been doing some I've been doing some research. Give me a second. I'm just looking up. I can't remember if I did too much else after yesterday's stream. I've been so okay, I was having this conversation with Gemini about like, oh, okay, if I like okay, so we took some time to learn about PWM stuff, and more specifically, or even more detail, like even going more lower level, I should say. Going even lower, we took time to learn how clock signals work and what clock signals are generated in the ESP32. So starting with the Xtal, which is our crystal oscillator. From there, the signal goes up to the PLL, where it gets multiplied. So a 40 megahertz signal gets amped up to 320 or 480 megahertz, and then from that point on, it can be sent to other places to do various things. And that high speed signal, it can further be divided down as need be. So, for example, with the CPU, you don't necessarily want the thing running at 480 megahertz. You might want it running at a much slower speed for various reasons, including saving power. So you can then have the speed set lower, and the hardware will manage the division of of this signal down to a lower frequency. And a similar thing happens with the APB as well. The APB clock signal gets, or clock source, the APB signal, let's just say that, is derived from the CPU clock. And even that gets further divided down because the APB is usually not supposed to be more than 80 megahertz. So we learned all of this stuff. That's great. And then after that, we went on to higher level stuff, which is where we started doing actual PWM stuff. We started using LEDC, which is our dedicated PWM hardware. Even though it says LEDC, it's more of a general purpose PWM hardware. And I was doing research on this as well. I was wondering that, hey, okay, so we've learned about LEDC PWM, and we've learned about MC-PWM, which is motor controlled PWM. Other than this, like, is there also like a much more generic version of PWM? Much more general purpose version of PWM? Are there other types of PWM hardware? And it turns out that LEDC is the general purpose PWM. Even though it says LED, it can be used for various things. And then you have motor control PWM, which is, it's much more geared towards motors. But I'm sure, given its working, you are not limited to motors if you have a very specific use case that just so happens to fit in with the way that motor-based or motor control PWM works. Then you can use it for that purpose. Also, so okay, we learned this, right? We got into give me a second. Let's just do this, and yeah. So we got into the code. We've written a bunch of code here. Um we created our timer. We also created the LEDC object. Uh then we created the timer that's using the LEDC object uh, to essentially grab the hardware timer. And then we also created a channel for that timer. So within within our, actually, I think for this, I should show the diagram that was shown here. That is this. So within the LED-C or LED PWM, we have two channels. We have the high-speed channel and the low-speed channel. Give me a second. Let me just make sure that, yeah, it's showing up. Okay. So within the LED PWM, we have the high-speed channel and the low-speed channel. And within each channel, we have 4 timers and 8 channels. So the timers are, well, the timers. The channels are our actual outputs. So this is where we're going to be outputting our signals from. And we have a separate set for high speed and a separate set for low speed. And I found out that apparently in later versions, because I was wondering why we had, like, in this function, we could only set this up, ls global clock source APB clock. And it turns out the reason for that is that apparently in later versions of ESP32, like in the S series and C series and so on, they don't really give you an option to customize the high-speed clock. The high-speed clock is just fixed, and everything else is the low-speed clock. So I think the low-speed clock can be customized maybe to a certain extent, but in this case, all we get is the APB clock as the low-speed clock source. So that's something I can explore later on. Now, okay, um, here's the dilemma that I ran into, is that we studied the low level of it, right? And then we came up to the high level to study the high level. And now in between this, I am kind of having trouble keeping track of everything. And Gemini said something interesting, because I started up a conversation with Gemini about this. And I was like, okay, so I've learned so-and-so thing. I went down to the low level. I learned, whatever there. And then I came up to the high level. I learned whatever there. And now I'm just kind of like, it kind of feels like I'm lost in terms of how I'm supposed to be thinking about these things. And wait, give me a second. Let me open up my chat on my phone, and then we can continue. Okay, so um, Gemini mentioned something very interesting. So first of all, Gemini presented this in a way that kind of helps me, you know, visualize this on a much higher level. And then Gemini mentioned something interesting that I feel like I need to remember at a later point. I don't remember if it's in this conversation or if it's in another conversation. Oh, okay, it's in this conversation. So after Gemini gave me like a 3-stage kind of way to look at it. Like, we have our clock source, which is the 80 megahertz clock. That's our APB clock. So we are not going any lower than that. We stick to APB clock. If we want to know why APB clock is 80 megahertz, then we can probably go lower. But like, just knowing that it's 80 megahertz is enough, right? Um, Here they mentioned that you have the choice. You can decide whether to use a high-speed clock, which is the APB clock, or the low-speed clock, which is RTC slash external. I haven't seen those options here yet. I think we'll have to explore that more. I don't know if that has something to do with this set global slow clock. Yeah, I don't know if this has something to do with it, because we are kind of deciding. I don't know if when we set APB clock to be the clock source, does that like apply to the entirety of the peripheral hardware that might be using APB clock at all? Because if that's the case, then like we would have to like keep that in mind when when we're working on when we're expecting different timings from various hardware. Yeah, I feel like that's something I need to look into later on. I actually okay, I'd asked a question to Gemini here. Wait, I don't know if I closed that conversation. LEDC. What was the thing I was talking about? Clock configuration. It's here. Okay, yeah. So, Gemini mentioned this. The hardware for ESP32 versus ESP32S and C series, the reason you only get a slow clock configuration is likely because of the specific ESP32 model you are targeting. In the original ESP32, the LEDC peripherals, the LEDC peripheral is split into two groups. High speed is hardwired to use APB clock, and low speed can choose between several sources. I feel like the multiple times that I've read this so far, I did not pay attention to this bit of detail. Yeah, I feel like I didn't fully understand that. So in high speed is hardwired to actually I did mention this at the beginning when I was talking about this, right? That Gemini said that high speed is apparently it's set to a fixed speed. So that's why you don't get the option to change it. But then in low speed, you can choose whatever you want. So we have APB clock, we have the RTC, 8 megahertz, which is a more low power sort of signal. And then we have Xtal, which is going to be 40 megahertz coming directly from the crystal. That being said, I don't think we've gotten an option here. Have we been? Wait, no, okay. There's LS clock source. Yeah, we do have an option here. For low speed, we have an option. I wonder if we have an option for, okay, it's just one. We do not get any more options. Give me a second here. This thing seems to be freezing at a horrible time. Oh, you know what? I'll do it from here. Yeah, we do not seem to be getting any more options. It's just APB clock. Okay. It's just APB clock. And in what about in the low clock source? Do we get anything here? Nope. Um, it's the same here. I guess that's all we get. I mean, internally probably there is an option, but like we don't get the option. Yeah, we don't get the option to do that. I'll have to see. Okay. Yeah, I'll have to see how we go about doing this. And then if this is the case, then why are we setting this? Why are we setting the global slow clock? What is the idea there? Because it says LS global clock source. Yeah, let me ask Gemini here. So okay, Gemini mentioned this. Let's continue reading the answer that Gemini gave. Because the high-speed channels are locked to the APB clock at a hardware level, there is no source selection function for them. They're always on. The set global slow clock function exists because the low speed group requires you to define its reference point. Okay, so internally, the high speed channel is hooked directly into the 80 megahertz bus, so no configuration is needed. But the low speed channel, because there you do have options, that's why we need to explicitly set a value. So it says in low speed channels, it passes through a multiplexer where you must choose between the high performance APB clock or the low power internal oscillators. Then, why ESP-HAL looks different? If you were using a newer chip like the ESP32S3 or C3, you would notice that the high-speed group has been completely removed by Espressif. In those newer chips, all channels are technically low speed, though they're still very fast, meaning you'll only find settings for global or slow clock sources. Right. Now, this brings me to the next question. Okay, so if um, okay, I also noticed that the enum LS Global Clock Source, LS Clock Source, no, LS Global Clock Source, CLK Source only has one option, APB CLK. Why even um, let us choose then when when there's only one option? I'm wondering if this is like a future proofing kind of thing. Like in the future, maybe we might have more sources, so let's make it an enum. Um, yeah, I'm not sure. Additionally, I'm curious about why, just a second. Um, yeah, I need to copy this. But first, let's do wrap so I can, yeah, okay, copy this entire thing, yank. As to why in the following code, I'm setting the clock source when the global clock source has been set. What's the difference and why am I setting two things? Okay, it feels redundant, doesn't it? This is a great example of how no STD Rust creates like ESP-HAL balance hardware reality with API consistency. Here is the breakdown of why you're seeing redundant settings and one option enums. The one option enum mystery. The reason LS Global Clock Source currently only shows APB clock for you is likely a combination of two things. Peripheral limitations. On many ESP32 variants, the slow clock is physically muxed uh, or connected primarily to the APB clock for stability. While the hardware can sometimes use the RC fast clock, which is the internal oscillator, that clock is often too unstable for precise PWM without calibration. Okay. And the other reason is HAL maturity. The ESP HAL is designed to be cross-chip compatible. Other chips in the ESP32 family might have 3 or 4 options in that same name. To keep that code structure the same across all chips, the developers use an enum even if your specific chip only supports one stable option right now. You know what? I think there might be a way to find out. Okay. All right. How do we, is it Control L? Yeah. Okay. So we are looking at, um, okay, definition references. Let's go take a look at the definition. There's only one. Clock source for LS timers. There's only one mentioned here. Is HS mentioned as well? For HS as well, there's only one mentioned. Hold on. Where am I? Though this does say ESP32, it doesn't mention the others. So I wonder if the code would be a little bit different if I were looking at the thing for ESP32 S3, C3, and so on. Yeah, this is something I should look into. This is something I should look into. Dude, at some point I need to. By the way, I was thinking about this yesterday. This was one of the things I was having a conversation with Gemini about, and I'm also now remembering one of the other things I was having a convo with Gemini about. So the first thing, I'm going to talk about the other thing first. Um, what I was thinking about was like, okay, I want to get into doing robotic stuff, but what if I wanted to, what if I wanted to give the robot sight without using a camera? Because I do have an ESP cam. I can use that, and that would be great in various ways. But what if I didn't want to do the cam method? What if I wanted to use other types of sensors? Like what are my options there? So Gemini was giving me suggestions for various types of sensors. Um, it suggested the what do you call it? The ultrasonic. Uh, I forgot what exactly the thing is called, but it's one of those things that it sends out like waves, and then it tries to read what bounces back, and based on that it decides where something is or how far something is. I Yeah, so that's one. Another one that it mentioned was some sort of IR related, infrared related distance sensor. It also suggested something that was a laser type of thing, and you get like these small modules for that as well. I looked it up. They're not that expensive, but for the time being, maybe I'll not go with that. There were also like one or two other things that were mentioned. Photo resistor, that was another one. And that, yeah, I'm gonna be using that. Definitely, I'm gonna be using that. I do need to order a couple of those as well. So I have the ultrasonic sensor, and I have the what do you call it? I have the ultrasonic sensor, and I have the photo resistor. I have a couple of other types of sensors as well, but I don't know how much they help in terms of giving the robot quote unquote sight. But yeah, that's one of the conversations I was having with Gemini, and the other one, oh yeah, the other one was about cheaper microcontrollers, because as I'm getting into microcontrollers more and more, and I want to do more and more projects with microcontrollers, I want to get the absolute cheapest ones that I can find, and I would also prefer for them to be as low power as possible, because I don't want to be spending too much on microcontrollers. I want to get them so cheap that even if I accidentally burn one, or short circuit one, or destroy one in some way, um, it won't really make that much of a dent. I want to get that cheap. Like I want to go that cheap in terms of microcontrollers. I want them to be disposable so that I can, apply them to whatever project I'm working on. Um, what was I saying? Oh yeah. So I looked into a bunch of different microcontrollers a while back. A chatter had mentioned, what was it called? CH32, I think. Yeah, I think it was called CH32 V003. Let me just, yeah, CH32V003. This is an incredibly cheap microcontroller. It's also low power. It has lower capabilities, but it's incredibly cheap. And if you have like super low power applications or applications that are not so demanding in terms of needing a decent amount words holy shit, in terms of needing a decent amount of processing. Let's say you don't need a whole lot of processing. You just need something that you can instruct it to do certain things and it's just going to do those things. um, then you can use one of these low power microcontrollers, and these are great for various things. First of all, for various, simple. I'm saying simple, but I'm fairly certain that you can do a bunch of even like sophisticated stuff with it. But like I'm gonna say simple. So in terms of if you have like simple DIY projects, you can use them for that. But also, if you're doing something like robotics, you can use these smaller microcontrollers to control very specific sections of your robot, because there might often be times where one microcontroller is not enough to control, every section of the robot. You need a couple of different microcontrollers, and as you start increasing the number of microcontrollers, your cost is now going up. Hold on, are we dropping frames? I think we're dropping. Oh no, okay, we're not dropping. Well, we did drop frames. Yep, we are dropping frames. Give me a second. I'm going to pause this. I'm going to pause this. And we are going to wait for the connection to stabilize, and then we're going to continue. Okay, I think we're good now. So, um, what was I saying? Wait, let me restart this. Okay, so, um, yeah, I was talking about, like, okay, when you are building a robot, there's probably going to be multiple microcontrollers involved. And as you start increasing the amount of microcontrollers, your cost is going to increase as well. It's not like I'm mass producing any robots right now, but then, it would be good to have these cheaper microcontrollers as well. And that was the sole reason why I started looking into it. And I did a bunch of research on it. I even found out about a Rust crate that that adds support for CH32 microcontrollers, and it specifically also has support for V003, um, the V003 line of CH32 microcontrollers. You do, however, need a programmer. You need a what do you even call what do you even call those devices? They're like debugging devices, JTAG slash debugger device. You can use it for two things. Well, you can probably use it for multiple things, but two things you can definitely use it for are flashing the program onto the device, and then also debugging the program as it's running on the device. By itself, you like, if you buy the chip by itself, you can't just connect it into your computer and flash your binary onto that CH32. It's not going to work, for at least for that specific one, the incredibly cheap low power version. For that, it's not going to work, so you're going to need a separate programmer. So as I was doing more and more research, I started to realize that I probably shouldn't be getting into this unless I absolutely need to, because it's going to introduce complexity. Because right now I'm studying how the ESP32 works, right? Then I'm also going to have to study how the CH32 works, and both of these have two different tool chains. They're not the same tool chain, though. I feel like CH32 probably has a RISC-V processor. I don't remember. Wait, processor. Give me a second, or well, give my internet a second so this Google search can complete, which for some reason is taking time. Okay, this is an ultra cheap RISC-V. Okay, this is a RISC-V processor. What was I saying? Yeah, so these are two different architectures. These are two different chips. They have different tool chains, and they also have slightly different API. Fortunately, they both the ESP side and the CH32 side, both of them build upon embedded HAL. So to a certain extent, the API is consistent. However, these are two different chips. And so the way that you program them is a little bit different. There is a tiny bit of a difference in the API. So all of these small differences here and there, they introduce complexity, complexity that I shouldn't be introducing unless I absolutely need to. And that's something I realized. Um, Sorry, zoned out. Com- so um, what was I saying? Yeah, I realized that this introduces complexity, and this complexity is something that I shouldn't be introducing unless I absolutely need to. Um, and right now, I don't absolutely need to. However, in doing my research, I did discover that we have CH32. We have the what is it called? I think it's called the RP 2040. Yeah, I think that's the name of the MCU, the chip, and the dev board for that is, I believe, the Raspberry Pi Pico. I think they do have different dev boards for that RP 2040. I can get cheaper ones as well. So that is an option. We have, first of all, the CH32V003. Then we have the basically any dev board that supports the RP 2040. Then we also have other options like the STM. I think it's called STM32. I think so. Those are more, at least from what I've read online, they are apparently more for industrial applications. They get used very heavily on that side. Um, and then I remembered that, okay, so I have an ESP32. I'm currently involved in the ESP32 ecosystem. I don't just have an ESP32, I also have an ESP32C3 Super Mini. And I remember when I was once doing research on the ESP32, or the difference between ESP32 and ESP32C3 Super Mini, Gemini was telling me that in the Super Mini, you do have various differences that make it suitable for low power applications, or rather, it's built with low power applications in mind. So I feel like that's a detail that I skipped out on, is the fact that I could just be looking for low power microcontrollers within the ESP32 family itself. And that would allow me to stick to, the library that I'm using, the current tool chain that I'm using, and it'll allow me to remain within the ESP32 ecosystem. How do I skip away from this? Wait, give me a second. My network is acting a little weird. Oh, it's in insert mode. I guess I just need to close this because I don't need to be changing the source code for the timer. Right. Okay, so you know what? Real quick, we're going to do something. I'm going to open up a new conversation with Gemini. But yeah, okay, that conversation that I had, about the different microcontrollers and my realization of like, oh, hey, why haven't I thought about the C3 Super Mini? All of that made me realize that maybe I don't need to be stepping away from the ESP32 ecosystem just yet. Maybe I don't need to branch out just yet until there's absolutely a need for it. And I'm glad that I learned about the fact that you can turn certain parts of the hardware off or certain hardware within the ESP32 off, and that'll conserve power. Like it it did not somehow, like, I mean, well, okay, not somehow, it's the fact that I don't know too much about it's the fact that I'm a beginner in ESP32, that's why I wasn't able to think about this. Sorry, zoned out. Yeah, it's the fact that I'm a beginner in ESP32, that's why I wasn't able to think about this. But I did not realize that, well, now I know about it, but like before knowing about this, I didn't realize that um in the ESP32, you can actually turn off certain portions of the hardware. So, for example, you have the PWM hardware, and then you also have the CPU hardware. These are separate hardware, like these are separate pieces of hardware. They can both be turned off, or well, the CPU can be turned off, and you can just use the PWM hardware. Apparently, you can also turn off the PLL, um, and all of this can be very helpful in terms of conserving power and um, also, well, mainly I'm worried about conserving power, so that's my main reason why I would be doing it. But yeah, you can like program the hardware. You can program the PWM to, which I'm assuming happens through like setting registers and stuff. You can program the PWM to behave a certain way, and then it's just going to keep doing its thing while the CPU goes to sleep, and it's not consuming a bunch of power because the CPU is not running. The PWM is running, which is it's gonna consume considerably less amount of power than whatever the CPU was gonna uh, siphon out of your battery. So in this way, you can have your battery. I forgot what the model number was, but the whatever your Lion battery is, you can have that one battery last for maybe months, depending on what your application is. You can have the thing last for weeks to months without needing to recharge it at all. Okay. So now I have two questions. So I need to open up two conversations and ask these questions before I completely forget. So I have ESP32 and ESP32 C3 Super Mini. Tell me the difference, aside from the fact that one is much smaller than the other. So that's the first question. The second question, which I'm already forgetting it. Oh yeah, okay. I'm learning about the ESP32. I'm still very much a beginner. I recently learned that you can turn off, or well, you can um, set the CPU in sleep mode and just let the PWM hardware continue running. And this way, you would be consuming much less power, leading to much longer battery life. I feel like I don't fully understand the concept of the multiple hardware working um, independently because I'm still new to ESP32 and MCUs in general. Tell me more about this and what other such hardware there is. So I know about a few things. I just want to see I just want Gemini to list out like all of those things. The ones that I do know about are from our research. There's the PLL, which is a separate hardware. There's the audio PLL, which is also a separate hardware. There's whatever the hardware for Wi-Fi and Bluetooth is. You don't need to touch any of that stuff if you're not doing it. And if you are doing it, then you definitely need a decent amount of power because those specific things apparently consume a lot of those specific things, as in the RF related stuff. The Wi-Fi and Bluetooth, they drink a lot of power. The PLL, turning it off can conserve some power. I don't know how much though. I guess Gemini will tell. Okay, so the first question, which was about ESP32 versus ESP32C3 Super Mini. While both are members of the ESP32 family, the Super Mini is based on the ESP32C3 chip, which represents a complete architectural shift from the original ESP32. The most significant technical differences are outlined below. The CPU architecture, the biggest shift. The original ESP32 uses the Extensa LX6 architecture. It is almost always dual core, allowing you to run your code on one core while the Wi-Fi slash Bluetooth stack runs on the other. The C3 Super Mini uses a RISC-V architecture, an open source standard. It is it is single core only. This means it handles tasks sequentially, though it is still very capable of running an RTOS or real-time operating system. Okay, then connectivity. Bluetooth 5.0. On the original ESP32, it supports Bluetooth 4.2 and Bluetooth Classic, useful for connecting to older audio devices or legacy car systems. On the C3 Super Mini, it supports Bluetooth 5.0. I think LE stands for low energy, but lacks Bluetooth Classic. However, Bluetooth 5.0 offers better range and modern mesh networking features that the original lacks. Then, power efficiency, deep sleep. The C3 is designed for modern IoT. It draws significantly less power in deep sleep, approximately 43, I think, microamps. I'm not sure. I don't remember my units. Hold on. Um, Amp units. Amp units, yeah, that's microamps. Okay. We can close this. Yeah, approximately 43 microamps versus 100 microamps plus on the original. So in the C3 Super Mini, it would be 43 microamps in deep sleep, whereas in the original ESP32, it would be 100 microamps. All right, then wake up latency. The C3 wakes up from sleep faster than the original, which is crucial for battery powered sensors that need to quote unquote blip a message and go back to sleep immediately. Then USB and flashing. One major quality of life difference is how they connect to your computer. The C3 Super Mini has native USB. This means the chip itself handles the USB communication, and the original ESP32 usually requires an extra chip. Yeah, that's a USB to UART thing. It usually requires an extra chip on the board to act as a bridge between the USB port and the ESP32. Which should you use? Okay, I think I'm good. So that answers that question. Then is our question about the hardware. So it's a bit of a light bulb moment when you realize the CPU isn't the boss of everything happening on the chip. That is actually a bit of a light bulb moment for me, because for a while I did not realize that that was the case, because coming from, computers, where the CPU definitely is the boss of everything. The CPU is what's controlling everything. Um, Coming from computers, I didn't think that that would be the case. So that was definitely a light bulb moment for me. In a modern microcontroller or MCU like the ESP32, the CPU is more like a manager, while the internal hardware modules are specialized technicians. The manager CPU can give instructions and then take a nap, while the technicians, which are the hardware peripherals, keep doing their specific jobs without needing any further supervision. Why independent hardware exists? In simple terms, the CPU is the most expensive part of the chip in terms of power. It uses a lot of energy to stay awake and process instructions. Hardware peripherals like the PWM controller are hardwired for one specific task because they don't have to think uh, because they don't have to think or make complex decisions. They can run on a very tiny amount of current. So PWM are LEDC peripheral. Then we have something called the ultra low power coprocessor. Wait, let's read the LEDC PWM. As you discovered, the LEDC or LED control peripheral has its own internal timer. Once the CPU tells it, flash this pin at 500 Hertz with a 50% duty cycle, the hardware handles the timing. Even if the CPU goes into light sleep, the hardware clock continues to pulse that pin. Then we have the ULP, ultra low power coprocessor. This is one of the ESP32 superpowers. Think of it as a tiny, extremely simple second brain that lives inside the chip. How it works. While the main high power CPUs are completely off or in deep sleep, the ultra low power, or the ULP can stay awake. What it does, it can read sensors like temperature or touch and check if a value hits a certain threshold. If it does, the ULP pokes the main CPU to wake up and handle the situation. Okay, that's interesting. I didn't know that was a thing. Okay, then other hardware that works while the CPU naps. Beyond PWM, several other modules can operate with varying levels of independence. Hardware timers, these are dedicated counters. You can set a timer to count down from 10 seconds. The CPU can go do other things or sleep, and will um, the hardware timer will fire an interrupt, an electronic alarm, to wake the CPU up only when the time is actually up. Then we have RMT, remote control peripheral. The RMT module is designed to send or receive infrared or LED strip signals. These signals require incredibly precise timing. If the CPU had to manually toggle pins, it would be stuck on nothing else. It would be stuck doing nothing else. Instead, the CPU dumps the data into a small memory buffer, says send this, and goes back to sleep, while the RMT hardware pushes the bits out. Then we have capacitive touch sensors. The ESP32 has internal hardware to detect touch on certain pins. You can configure these so that the chip stays in deep sleep until someone actually touches a button. I should keep that in mind actually. That would be really great to wake the CPU up. Yeah, yeah. Um, okay, sleep until someone actually touches it. The CPU isn't checking the button. The hardware is waiting for a change in the capacitance to trigger a wake up. Then we have the power hierarchy. Okay, okay. All right. Okay. Help me understand how the PWM hardware knows what to continue doing after the CPU has gone to sleep. Is it that there are certain registers, and this is actually, I'm genuinely curious about this, whether there are registers within these dedicated, hardware things, hardware modules. Within these dedicated modules, do they have their own registers and their own like tiny, in a way, tiny processors that not exactly processors, but like because these modules are hardwired to do specific things, right? Maybe they're also hardwired to read certain registers and do stuff based on that, or like what's the idea there? Let me ask the question. Is it that there are certain registers even within these dedicated hardware modules, and the modules are hardwired to read these registers and take actions accordingly? Or is it something else? Okay, you hit the nail on the head. You've just described the fundamental architecture of almost all modern microcontrollers. It is exactly about hardware registers, but there's a specific physical trick that allows it to work while the brain is asleep. Okay, the post-it note analogy. Think of a hardware register like a physical post-it note stuck on a machine, stuck to a machine. When the CPU is awake, it writes instructions on that note. Example, frequency equals 1 kilohertz, duty cycle equals 50%, and so on. Once these bits are flipped in the register, the PWM hardware doesn't need to ask the CPU for permission anymore. It simply looks at the state of those physical switches, which is the registers, and stays in that state until something changes. Why doesn't the memory vanish? Why doesn't the memory vanish when the CPU sleeps? This is the key. The ESP32 is divided into different power domains. The core domain contains the high-speed CPUs. This can be completely powered down to save energy, and then the peripheral slash RTC domain contains the registers for things like PWM, timers, and the ULP. When you put your chip into light sleep, the power to the CPU is cut or throttled, but the power to the posted notes or registers for the PWM hardware remains on. Since the hardware is made of logic gates that are hardwired to follow the values in those registers, the PWM signal keeps pushing, keeps pulsing. The role of the bus. To understand how they talk, you should know about the internal bus. The CPU and the hardware modules are connected by a communication highway called a bus. The CPU sends the CPU sends a write command across the bus to a specific address. Give me a second. My fans are going crazy here. I'm just gonna shut off the RTMP feed for maybe like a couple of minutes. Okay, all right. So it sends a write command across the bus to a specific address, which is the PWM register. The PWM hardware receives that data and stores it in its local latch, a type of memory that holds its state. Once the data is latched, the CPU can literally be disconnected from the bus or powered off. The PWM hardware is now self driving. Then we have the clock, which is the heartbeat. This is one gotcha you should know. Even if the registers are powered, hardware needs a clock signal, a heartbeat, to actually move. If you put your ESP32 into deep sleep, it usually turns off the high frequency crystal oscillator to save maximum power. If the clock stops, the PWM stops, even if the registers still have the instructions. This is why light sleep keeps certain clocks running, so PWM continues, and deep sleep shuts down almost all clocks. PWM usually stops here unless you are using a specific low power RTC timer. Then, other independent hardware behaviors. Since you are curious about other hardware that acts this way, here are two fascinating ones. Direct memory access. Actually, we have an example for DMA, direct memory access. That'll be interesting to get into later on. I think it gets covered in this tutorial as well. Give me a second. Let me just scroll this list. Okay. Buzzer, voltage divider, ultrasonic, PIR sensor. PIR sensor was one of the distance sensors that this one was talking. Actually, was it distance or motion? Okay, now that it mentions motion detection, I'm realizing that maybe I was remembering wrong. I do have a PIR sensor. It looks like at least mine, looks like a half dome shaped thing. Let me open this up so I can show you guys. But also, let me keep scrolling. ADC, LDR, Wi-Fi, I2C, OLED, thermistor, SPI, SD, RFID, joystick, Bluetooth, LCD, e-ink, so and so, so and so. Okay, DMA might be a part of one of these things. It might be somewhere within one of these things. Yeah, I'm gonna have to look for this later on. Actually, okay, DMA is not mentioned here. However, there is a DMA example in the official examples in the repo. There is DMA mentioned. There's actually a bunch of other stuff mentioned as well. Okay, anyways, let's continue reading this. So, direct memory access. This is the ultimate independent worker. Usually, if you want to move data from a sensor to the memory, the CPU has to pick up every single byte and move it. With direct memory access, the CPU says, "Hey, DMA, take the next 1,000 bytes from the radio and put them in this folder. Wake me up when September ends. Wake me up when you're finished." Okay, the CPU then goes to sleep and the DMA hardware moves the data byte by byte in the background. That is crazy. Hold on, dude. Okay, that is interesting. That is very interesting to know because that does kind of change things a little bit in terms of because like I was actually concerned about this thing like how are we gonna store state, how can we manipulate data um, when the CPU is off, so are we limited to just having to wake up the CPU, have it do the work and then put it to sleep again, or is it that is there some other way? And it turns out this might be that way. This might actually be that way. Uh, which mouse am I using? This one. Okay, then I2S. Inter IC sound. If you are if you are playing music, the I2S hardware can pull all audio data from the memory and quote unquote stream it to a speaker continuously using its own timing hardware, allowing the CPU to only wake up occasionally to refill the data buffer. Holy shit, dude. Okay, cool, cool. All right, I can start up the thing now. I actually don't need to start it up even now. I probably shouldn't have started up the RTMP stream. It's okay. I've started the thing up. I'll just continue with this. Um, Continuing with the question I was asking to Gemini, I asked this question about the enum. Okay, so oh yeah, this is where I'd gotten distracted. So other chips in the family, in the ESP32 family, might have three or four options in that same enum. Same enum in this case being the LS clock source, and probably also HS clock source. To keep the code structure the same across all chips, the developers use an enum even if your specific chip only supports one stable option right now. Think of it as a placeholder for portability. If you swap your code to a chip that supports an external extal for PWM, the API won't break. You'll just see more options in that enum. Then global clock versus timer clock. So this was my second question, which was why am I setting? Let me come back here. So if we look at LS timer here, we can see I'm setting the clock source here. We have to set the clock source here, but then we are also setting the clock source here. So like, what's the idea? Because one says global clock and the other just says clock. Sorry, zoned out. Okay, where was I? Yeah, this is the two-stage configuration process of the LEDC peripheral. It helps to visualize it as a series of water valves. So stage one is the global clock. This sets the source for the entire low-speed group. So I'm assuming by low-speed group they mean let's come back here, close this. I did open the PIR sensor thing, so let's take a look. This is what I've got. I've got this uh, possibly this exact one, maybe like a few tiny differences, but this is the dome I was talking about, the half dome kind of. I think a dome is a hemisphere basically. Um, Wait, is a hemisphere like half a sphere, or am I do I have my terminology mixed up? Yes, a hemisphere is exactly half of a sphere. It is formed by cutting a 3D sphere into half. Okay, that's all I need to know. Right. So, um, this is the PIR sensor, and this is apparently used to detect motion. I might order a couple of these. Now that I'm thinking about it, I might actually order a couple of these. I have my shopping list up here somewhere. Hopefully I have not deleted. Yeah, I haven't deleted it yet. I actually no, this is not the list I was talking about. This is not the list. Um, my list is here. Yeah, okay. I completely forgot that I'd actually added the Raspberry Pi adapter to that. Unfortunately, I might need to take it off as well because I don't think I have enough money for that. There is some other stuff that I want to buy as well. So I'm gonna have to like pick and choose which specific one I wanna, go for. Um, Sorry, zoned out. What was I gonna? Oh, PIR sensor module. I'll see if I want to buy more of these. I'm still not like entirely sure. I do want to buy like one or two OLED displays. Um, Surprisingly, I never added them to the list. Why didn't I do that? I wanted to buy like one or two OLED displays. Let's add it to the list. I'll see. Because these are nice and cheap, like small, cheap displays. I can get like tiny square shaped displays for various purposes. Okay, all right. Back to this answer. Where was I? Yeah, so stage one is the global clock. This sets the source for the entire low speed group. So moving over here, I'm assuming it's talking about this group, like low speed channel. Maybe I could be wrong here, but let's find out. Okay. Purpose, it decides where the entire LEDC peripheral gets. Okay, the entire LEDC peripheral, is that plus the low speed or minus? No, is that plus the high speed or minus the high speed? As in, is the high speed channel included or is it only the low speed channel? Sorry, zoned out. Okay. Um, Purpose. It decides where the entire LEDC peripheral gets its raw material, quote unquote, raw material from, or the clock signal from. Impact. If you change this, every single low speed timer, that answers my question. Okay. If you change this, then every single low speed timer and channel is affected. You are essentially turning on the main pipe for the whole system. So in this case, we are saying that we want the main clock source to be APB clock. This also means that we probably don't get a choice. We don't get to choose any other, like, we have APB clock here, and that's going into peripherals. We are not getting a choice for any of the other stuff. Uh, yeah, I wonder what happens in the case of APLL clock, or in the case where maybe you want to use the XTL clock instead. You just want the XTAL's raw clock signal. I I don't know if we even have those as options available or not. But okay, that's stage one. So we are deciding that we want our LEDC peripherals clock source to be APB clock. Okay, cool. Then um, then we have stage two. Stage two is the timer configuration. That's the clock source. Even though you told the peripheral to use the APB clock, the individual timer needs to know what it's looking for. Purpose in Rust, this is largely for validation and math. The configure method needs to calculate the divider. Divider equals F input divided by F target to hit your requested 24 kilohertz. Because in my case, the example code that I'd given was 24 kilohertz for, I think it was for the low speed. I don't remember. Hold on. What conversation is this? This is a different conversation. I gave the code for low speed. So the low speed one, it mentions 24 kilohertz. Right. Going back down. Okay, the configure method needs to calculate the divider. Divider equals F input divided by F target to hit your requested 24 kilohertz. Okay, so this answers a question that I had previously, which is who is calculating the divider? Is it me, or is that being calculated in the function? Turns out it's being calculated in the function. Okay, the logic. To do that math accurately, the timer needs to know exactly which source it is drawing from. Why do I have to set it twice? In the underlying hardware, the timer has a multiplexer that selects its input in the underlying hardware. It has a multiplexer that selects its input. The input can come from, right, so we are looking at this diagram here. I wonder if any of the later diagrams help. Are there later diagrams or is it just tables? It's mainly tables. It's this diagram that helps the most. Okay. All right. In the underlying hardware, the timer has a multiplexer that selects its input. Even if the global setting only offers one choice, the timer's hardware register still has a bit that says, look at the global clock source. By passing timer ls clock source APB clock into the configure block, you are confirming to the HAL which source to use for the math, and you are setting the register bits that point that specific timer to the clock source. Summary of the flow. Okay, you know what? That is satisfactory enough for me. Now we're going to continue with that little dilemma that I was having of how I should be um, conceptually on a higher level. How should I be looking at this? Give me a second here. I'm just loading something up. And once that's loaded, I can continue reading. Hold on a second. Right. Okay. So, Gemini. Okay. So my question. I don't think I'm going to read out the entire thing, but like just to give you an idea of like how like the issue that I was having. I mentioned to Gemini that yeah, I took the time to learn how this stuff works on the lower level because I was curious about how it's working and what a clock signal is, what is being done with the clock signal, um, how the clock signal is processed in different ways, what different hardware processes the clock signal, how the clock signal gets transformed, what different forms it gets transformed into. You have the XTL clock, the PLL clock, the CPU clock, the APB clock, and so on. Right. So that's the low level stuff. right? That's how things are working on the hardware level. And then now we are on the higher level, we are on the software level, on the coding level, where we have set up this PWM logic. But then I'm having trouble deciding how I should be looking at this because there seems to be way too much going on. And I'm having trouble like keeping track of the things. So I need to, and this is where Gemini's second response in this conversation really helped me because Gemini mentions later on, I'll read that second response later on as well. But Gemini mentioned this: in engineering, we use abstraction layers to keep from being overwhelmed. That that part is really, I feel like that's gonna, I feel like I should remember that for the future. I should try to find abstractions wherever possible. I should still try to understand things on a lower level because of my curiosity and wanting to understand how things work. But if I have to trace the entire signal back all the way to XTL or sorry, XTAL or PLL or CPU, if I have to trace the signal all the way back each time I want to do a calculation, it's going to get very confusing for me. So for the sake of simplifying the calculation, I think at this point, now that I know why the signal is 80 megahertz, I can just stick to the fact that, okay, APB clock is our source. And actually, in the code itself, we don't have any other options. We mainly only have APB clock. And I know that APB clock is, um, I know that APB clock, sorry, I zoned out. Um, I know that APB clock is 80 megahertz, so that we can just stick to that. That's going to be our base frequency, and all the other calculations that are being done, they're being done on top of this. So then that becomes our abstraction. Right. So let me read out what Gemini said. Actually, let me also mention the question. I mean, I've described the question already. It was basically a dilemma where I wasn't sure how I'm supposed to be thinking about this. Um, yeah, so what I was saying to Gemini was this. I said, okay, now that I've learned that being the low level stuff, and I've produced a simple LED fade effect using PWM, which is our high level stuff, I'm trying to further explore the math being used to make this happen. And I'll get there eventually. But I feel like in between all this, I've kind of lost the high level conceptual thought process that I need to be following here when it comes to programming the ESP32 for PWM signals. My mind's all over the place. I'm not necessarily looking for help with understanding the math. That might be another conversation that I might have with you. I'm more so looking for the way to think of things conceptually on a higher level so that I can do PWM things while still understanding how things work, but also being able to build things using various PWM features. And then I was like, anything you can tell me here to help me out? And then Gemini said this: it's easy to get lost in the clock tree forest, which that's true. It is kind of a forest. When you're working with the ESP32, when you're working with ESP32 and no STD Rust, I feel like, okay, I've realized this. Um, when I tell Gemini that um, I'm programming the ESP32 using no STD Rust, by default, like if I just say these things, specifically these things, nothing more, then Gemini assumes that I'm controlling individual registers. And so it probably assumes that I'm doing something that is kind of the equivalent of assembly programming, but like not necessarily, assembly instructions, but kind of the equivalent of that. So writing things to registers and invoking certain instructions and stuff like that, it probably assumes that I'm doing something along those lines. Um, but then I have to mention to it. Actually, I don't even know how the assembly side of things goes for, or rather, the instructions side of things goes for ESP32 processors. I'll have to look into that later on. For now, I don't want to dive deep into that because it's not going to benefit me at all. What it is going to do is eat up a bunch of my time for the sake of my curiosity. I need to get much better at recognizing this. Holy shit. My curiosity is, in terms of these very complex things that I'm learning, my curiosity about how things work, unless I keep control over it, I end up going way too deep into it, and then I end up spending a lot of time on it. Okay, all right. It's easy to get lost in the clock tree. Oh yeah, what was I saying about Gemini? Okay, so Gemini, if I just mentioned that I'm programming the ESP32 using no STD Rust, Gemini kind of assumes that I'm writing to registers individually. But then if I mention using ESP HAL, then Gemini understands that, oh yeah, there's a higher level that this person is doing. So then Gemini assumes that, oh, okay, it's not register stuff. It's much more higher level than that. There's a whole bunch of like function calls and structs and stuff like that. But yeah, that's a small observation that I made with uh, like having this conversation with Gemini. Right. You've correctly identified the physical chain that is extal to PLL to APB to peripheral. Okay, great. But when you're actually programming, actually, there's one, hold on, there's one more thing that I was curious about. It's this thing. Because I had a conversation with, I had a separate conversation with Gemini about this. Um, it was about like, where is the APB clock actually coming from? Because I'm still confused about whether the APB clock comes from the PLL. So there's like division happening. There's definitely division happening for sure. But like, where exactly is that clock signal coming from? Is it coming from the CPU hardware, which is where it would be based on the CPU clock? Or is it coming from the PLL hardware, which is where it would be based on, the PLL clock, and the division would happen accordingly. Now, another conversation that I had with Gemini, in that Gemini mentioned that it's derived directly from the CPU clock. So it mentioned this. To answer your question, to answer your specific question, the standard route for high performance operation is extal to PLL to CPU clock to APB clock. Here's how the signal flows and divides. From the extal, it's a 40 megahertz signal. This is your base reference. This goes to the PLL and turns into, it gets multiplied into a 320 megahertz or 480 megahertz clock signal. And then from the PLL, the output is divided down to your desired CPU frequency, which could be 240 megahertz, 160 megahertz, or 80 megahertz. And then the APB clock is then derived directly from the CPU clock. The division logic, you mentioned the 80 megahertz standard for APB. In the ESP32 architecture, the APB clock has a strict requirement. It cannot exceed 80 megahertz, and it must be a rational division of the CPU clock. So I'm assuming it has to be like divisible by whatever the CPU clock is. Or the CPU clock has to be divisible. Yeah, it has to be divisible by the CPU clock. Right. Um, Sorry, zoned out. Okay, it cannot exceed 80 megahertz, and it must be a rational division of the CPU clock. The hardware uses a divider, often referred to in the TRM as pre-div, to bridge the gap between the high-speed CPU clock and the peripherals. So then it mentions that, okay, if the CPU clock is so and so, it uses so and so divider. If it's so and so, it uses so and so divider. And if the clock speed is already 80 megahertz, it's just going to use a divider of one. So it's just passing the value through. Then I asked another question. I said, okay, wait, so when we say APB clock is derived from the CPU clock, is there a physical line going from the CPU to APB? And then Gemini responded with, it's less of a wire coming out of the CPU and more of a sequence of gates in the clock control module. In hardware terms, the CPU doesn't generate the clock for the APB. Rather, they both drink from the same fountain, but the APB has a specialized filter, which is the divider. The hierarchy of the clock tree. This is a series of valves on a high pressure pipe. Think of it as a series of valves on a high pressure pipe. You have the source, which is the PLL. This is a high pressure. This is the high pressure main line, which is 320 megahertz or 480 megahertz. Then you have the CPU divider. This is a valve that taps into the main line and scales it down to say 240 megahertz. This signal is then routed to the CPU core. Okay. Um, the APB divider. This valve sits downstream of the CPU's valve. It takes the 240 megahertz signal and divides it further by 3 to produce the 80 megahertz signal. Then the physical routing. In the ESP32 silicon, this happens inside the RTC control or the APB control peripherals. This is the physical trace on the die that carries the CPU clock signal into a prescaler, a hardware counter. The output of that counter is what we call APB clock. This specific parent-child relationship is why APB clock is often called a subsidiary clock. Why no STD developers use it? Okay, the summary. PLL goes to the CPU selector mux, which then gives us our CPU clock, which then goes into APB div and gives us the APB clock. Yeah. So while there isn't a line coming out of the CPU box on a block diagram, the APB clock is physically hardwired to be a function of whatever the CPU clock is currently doing. If the CPU clock stops, the APB clock stops with it. That is vital information. That is definitely very important information. Okay, then I asked a question further saying if I'm using no STD Rust for the ESP32, using ESP-HAL and the like to do higher level stuff using PWM, do I need to concern myself with all these details, or is there a base level of understanding I can maintain and build all other info up on? Then Gemini said, when using ESP-HAL and when using ESP-HAL in a no STD environment, you've hit the sweet spot of the embedded development. You have the power to poke every register, but the HAL is designed so you rarely have to. For things like PWM, using LEDC or MCPWM peripherals, you can absolutely build on a base level of you can absolutely build on a quote unquote base level of understanding without getting bogged down with which clock tree without getting bogged down in the clock tree every time. Sorry, zoned out. The base level mental model. In ESP HAL, you can treat the clock system as a provider and the PWM as a consumer. The provider, clock control, during initialization, you define your system clock once. Sorry, zoned out. What was I? Where was I? Yeah, you define your system clocks once. The HAL takes your desired CPU speed and calculates all the messy division logic we discussed earlier. Calculates all the messy division logic we discussed earlier, setting the APB, setting the APB to 80 mega. My God, I'm having trouble reading. Setting the APB to 80 megahertz and configuring the PLL. The consumer, PWM. When you initialize a peripheral, hold up. Setting the APB to 80 megahertz and configuring the PWM, sorry, the PLL. The consumer. When when you initialize a PWM peripheral, you don't manually calculate the APB division. Instead, you tell the HAL, I want a 20 kilohertz signal. The HAL then looks at the current APB clock. Okay, this is getting back to our code. I'm glad that I continued reading. The HAL then takes the HAL then looks at the current APB clock, which it already knows is 80 megahertz. The HAL then looks at the current APB clock, which it already knows is 80 megahertz because it set it up, and handles the math for the PWM specific prescalers for you. When do you actually need the deep info? You can ignore the clock tree details 90% of the time. You only need to pull the knowledge out of your toolkit in three specific scenarios. Extreme frequencies. If you need a PWM frequency that is very high, close to 40 megahertz. Oh, a PWM frequency. For a second there, I was confused because I was like, hold on. Um, I was like, hold on. I thought we were already at, higher frequencies and stuff. How is 40 megahertz high? But no, for a PWM frequency, that's high. Okay, where was I? Okay, if you need a PWM frequency that is very high, close to 40 megahertz, or very low, sub-hertz, I actually was considering going down to the hertz level because I was curious about that. I wanted to see if I can set a very low. Actually, okay, we can try that right now. Like right now. I wanna see what happens. I actually okay. I wanna see if we can do something here without setting like a duty fade thing. Like what if is there anything where I can just set the pin to be like to just send out, you know, yeah, let me ask Gemini this. I'm doing ESP32 programming using no STD Rust with the ESP HAL. I'm learning PWM stuff for the sake of looking at the signal. Yeah, for the sake of looking at the signal, I'm wondering if LEDC allows me to um, do something where I just set the pin to give out um, uh, say, I don't know, 5 hertz signal, so I can actually see the LED pulsing on and off. So far, I've used start duty fade. Is that what it's called? Yeah, start duty fade. But that's more for setting a timer-based thing. Okay, it is absolutely possible to do this with the ESP32's LEDC peripheral. While start duty fade is great for smooth transitions, what you're looking for is a standard fixed PWM frequency and duty cycle. To see an LED pulse visibly at 5 hertz, you simply need to configure the LEDC timer with a low enough frequency and a 50 and a 5% and a 50% and a 50% duty cycle. In no STD Rust, with ESP-HAL, the LEDC peripheral uses a tiered configuration. You use the source clock, usually the APB clock. You use a timer. You set the frequency, example 5 hertz. Okay, so I was concerned that 5 hertz would be way too low, and so I wouldn't see any difference. But it turns out that might not be the case. You know what? Let's do that with our, what did I set the GPIO 12 is going to the red LED. So that is our high-speed timer. So what would I need to do then? Actually, yeah, okay, wait. Have we mentioned like starting? Okay, so we configure, set up the channel. Oh, there's a set duty function. Okay, let's take a look. Let's take a look. There's start duty. Oh, there's set duty. Set duty, and this takes in a byte, an unsigned byte. That's interesting. Okay. So then I wouldn't be doing this in a loop because it should be like a constantly oscillating signal, right? Um I'm hoping I've got this right. So let me try hold on. My thing is stuck over here. Huh. Okay. Right. Duty percentage. We're not specifying the time here. We're specifying the time in the timer. Okay, we can set the, okay, 1 bit is not okay. 2 bits works. 2 bits is not okay either. 3 bits. 3 bits. We need 3 bits. So we're going to do 3 bits. I'm wondering if I have set it to 6 bits, would a low level work or not? Like, would that cause a problem? So let's say from hertz, let's say 5 hertz. And here we don't do this. Oh God, wait, stop. Yeah. Here we don't do this. Instead, we do, oh, wait, wrong one. My bad. This. So we comment this out. We are not doing anything in the loop. Before the loop starts, we do hs channel dot set duty. I still don't understand what. Oh, duty percentage. Wait, we are setting. Okay, so I guess we started at 100, right? Duty. The percentage is assigned byte. Are they expecting 255 as 100, or is 100 accepted as 100? I'm not sure. Let's flash the thing. Let's see what happens. So this should affect our red LED. Yeah, it it doesn't it doesn't work. I am doing something wrong here. Let's try setting it down to 3 bits. We have HS timer, HS so and so, duty percentage. I don't understand if we have a duty percentage mentioned there, then what is this for? So like, okay, let's try 255, I guess. It's an unsigned byte, so should be 255 should be fine. I also noticed that the blue LED is not doing anything, or rather, it's not doing its. Or was it? I don't remember. Hold on. I guess we'll. Yeah, the blue LED is not doing anything. There's something wrong here. There is something wrong here. Does it ever make it to? Okay, let's try yanking this and putting it here. And um that should run for only 1 second, right? So at the very least, we should see one iteration. Yeah, at the very least, we should see the LED glow once, the blue LED specifically. I'm not sure if that worked. Hold on, I can't tell if the LED is becoming brighter gradually or if it's just stuck at one thing. Oh, I can reset. Okay. So this is interesting. Well, the first might be a floating pin thing. The second time that it becomes, uh, yeah, the second time that it becomes lighter, something is off here. Something is definitely off here. Let me see what Gemini's. Oh, I have to unwrap it. I keep forgetting that I'm in Rust, dude. I keep forgetting. I should always check the return type and then decide what I do based on that, because the return type here is result, and a result needs to be unwrapped. Otherwise, you can't do anything with it. Which is interesting because the unwrapping of this is what seems to do something. I find that kind of interesting. Yeah, I find that kind of interesting. Oh, wait. Okay, let's try running this first. I'm wondering if I need to do this thing like while HS channel is duty fade running. I could set it up. Let's say while HS channel dot is duty fade running. HS. Oh, we are on replace for some reason. HS channel dot is duty fade running. We do this. In the meantime, let me take a look at Gemini's. Also, did I add in? I don't know if it ran. Yeah, it didn't. It didn't run. It did not run. What did Gemini suggest for values? 512. 512 is half of 1024. But then here it says 8 bits. Here it says U8, doesn't it? Did I get that wrong? No, it says U8. So like if I did this, yeah, that's an error. Yeah, I'm not sure. I'm gonna have to look into this. I need to try different types of values. I don't know. Let's try setting it to 0. See if that works. Oh, wait. Is it sending out a pulse or not? Like, is it constantly sending out a pulse or is it just like a one-time thing? Dude, I just realized that. Like, okay, what if I do this? Okay, and then I change this to this, and then yank, and then okay, okay, let's not do that. Right. So we're gonna try this because I don't really know what's going on here. Yeah, still nothing. Nope, still nothing. Okay, I'm gonna have to continue reading up on this. I think I'll continue reading up on this, or I might go back to my Western research because that is equally important. Actually, we've made some good progress here today um, in terms of understanding how I should be approaching this. So I'm going to continue reading up on those specific things. I'm not going to continue with trying to solve this problem. We'll solve this tomorrow on stream. Um, but I will go back and read the conversation that I'm having with Gemini about the way that I should be approaching this conceptually. Like, what kind of mental model should I be building when I'm thinking about this? And I need to do something that I need to follow a path that prevents me from going way too deep into the lower level stuff and like complicating things for me. So I'll do that. But yeah, for today, I guess I'm gonna go back to the Western stuff. I need to continue with the Forrest Mims book as well. I don't want to leave analog electronics. Like that was getting interesting as well. So I need to do there's a bunch of the stuff that I need to like there's a bunch of backlog that I have to clear, basically. But that's going to be it for today's stream. I don't think I'm going to be raiding anyone. I'm just going to end the stream and go and eat something. And then I have a bunch of this research to do. So I'm going to do that. Yeah, that's going to be it for today's stream. I hope you guys have a nice day, and I'll see you all next time. Peace.